Okay, here we'll take a look at 2007 AP Calculus AB free response question, Form B of the exam, problem number 6. This is a non-calculator question, and they start by telling you that you have a twice differentiable function, meaning that f has two derivatives that exist everywhere, and they tell you that f of 2 is 5 and f of 5 is 2. Then they go on to say something about this function g. They define g right here. That's not going to be needed in part A. We'll need to refer to that in part B. In part A, all we need is this first sentence. So part A says, explain why there must be a value c in between 2 and 5 such that f prime of c equals -1. So if you think about where we've seen this f prime of c business before, in the mean value theorem, f prime of c is the left-hand side of the conclusion of the mean value theorem. So what the mean value theorem said was if we have a function that's two things, if our function is continuous and it is differentiable, which just means the slope of the tangent line exists everywhere on the interval from a to b, then there's some number c in between a and b. So if you think back to what this question said, it said c had to be between 2 and 5. So 2 and 5 would be serving like our a and b, such that f prime of that c value equals the slope of the secant line connecting the endpoints of that interval. So all that said graphically was if you have a function that's continuous and differentiable, as you go from this point on the graph to this point on the graph, if you find the slope of that secant line, you're guaranteed that there's at least one value c in between the endpoints of your interval where the slope of your tangent line was equal to the slope of that secant line. So in part A of problem number 6 here, what we can say is since f of x is twice differentiable, I'm just going to abbreviate that. I don't want to write that whole word out. Since f of x is twice differentiable, it is both continuous and differentiable. If the second derivative exists everywhere, the first derivative has to exist everywhere. And if the first derivative exists everywhere, you know your function's continuous. We had a little theorem that said that. So since our function is twice differentiable, it has to be differentiable everywhere, and since it's differentiable everywhere, it's also continuous everywhere by default. So it is continuous and differentiable. And so since we've explicitly stated these things, we know we can use the mean value theorem at this point. Okay, we said that the function is continuous and differentiable, and we said why. Since the second derivative exists everywhere, we know our function is continuous and differentiable everywhere. Why must there be a value c in between 2 and 5 such that f prime of c equals -1? Well, I'm guessing if we find the slope of the secant line on the graph of f connecting the point 2 comma 5 with the point 5 comma 2, we're going to get a slope of -1. So if I take f of 5 minus f of 2, so that would be the difference in my y values, and over the corresponding difference in x values, 5 minus 2. Well, they tell us that f of 5 is 2, so I'm going to put 2 in place of f of 5. They tell us that f of 2 is 5, so I'm going to put 5 in place of this. So 2 minus 5, 5 minus 2 is 3. 2 minus 5 is -3. And if you reduce that, you get a value of -1. So if the slope of the secant line is -1, and you know you're able to use the mean value theorem because the function is continuous and differentiable, by the conclusion of the mean value theorem, and I'm not going to write this out, I'm just going to state it, by the conclusion of the mean value theorem, there must be a value c in between 2 and 5 where the slope of your tangent line or the value of the derivative equals the slope of that secant line. If I click ahead here to part B is a little bit different because now you're dealing with the function g of x. It says to show that g prime of 2 equals g prime of 5. So they've defined g of x right here. If we want to know g prime of 2 and g prime of 5, we're going to have to find g prime of x first. So g prime of x is just going to be an application of the chain rule because we have an outer function f and an inner function f. So this is kind of a goofy application of the chain rule. The derivative of the outer function would be f prime, and then we're going to leave the inner function inside of that. So we have f prime of f f of x, and then finish the chain rule, multiply by the derivative of your inner function. Your inner function is f of x and has a derivative f prime. So here's g prime of x. You want to show that g prime of 2 equals g prime of 5. So take a minute to compute g prime of 2. So g prime of 2 is going to be f prime of f of 2, just putting 2 in place of the x's and g prime of x, times f prime of 2. And let's see, we know that f of 2 is given, right? F of 2 is 5. And so if we take what f of 2 equals, 5, and put it in place of f of 2, we have f prime of 5 times f prime of 2. Now we don't know what f prime of 5 is, but we don't know what f prime of 2 is, so we can't really go any further with this. What we can do is we can try to compute g prime of 5 using the exact same method. G prime of x is this, so we're just going to put 5 in place of the x's in that derivative. So g prime of 5 is going to be f prime of f of 5 times f prime of 5. And like we said about this calculation back here, we didn't know what f prime of 5 was, so this is going to have to stay the same, but we do know what f of 5 is. F of 5 was given. F of 5 is 2, so I can put 2 in place of f of 5. So this ends up being f prime of 2 times f prime of 5. Now if you compare these two results, although we don't know the numerical values of them, since multiplication is commutative, these two calculations are obviously equal to each other. So we've basically shown that g prime of 2 equals g prime of 5. Now it says use this result to explain why there must be a value k in between 2 and 5 such that g double prime of k equals 0. So this seems kind of similar to what we had going on in part A. The main difference is it's saying something about g double prime of k being equal to 0. But we do have this value in between 2 and 5 still. So it seems kind of similar to what we did with the mean value theorem in part A. But how do we make sense of the second derivative here? Well, even though the mean value theorem, the way it's stated on this screen, it's applied to the function f, if you wanted to apply it to the function g double prime, you could say g double prime of k equals, now this is the second derivative, so the function values would be generated by the first derivative here. So I've basically, changed the conclusion of the mean value theorem to incorporate a second derivative. So as long as our derivative is continuous and differentiable, we're going to be able to use this version of the conclusion of the mean value theorem. So if we go back to what we have so far for part B, can we confirm that g prime, because that's the function we'd be applying the mean value theorem to, that's the function where we have the function values coming from here. So can we apply the mean value theorem to g prime? Well, is g prime continuous and differentiable? Well, let's see. F prime is continuous. F prime of f of x, which is also continuous, is continuous. And the product of two continuous pieces would also be continuous. So I'm not going to write this out, but based on what we just said there, yes, g prime is continuous based on how it's defined. Is it differentiable? Well, if you took a derivative of this, that's just going to give you some f double primes. You're going to have to use a product rule and another chain rule. But since the second derivative exists everywhere, f is twice differentiable, you know that g prime is going to have a derivative that exists everywhere. So with that said, yes, g is continuous and differentiable. So by the conclusion of the mean value theorem, if we found the slope of the secant line on the graph of g prime, we'd take g prime of 5 minus g prime of 2 over 5 minus 2. Well, g prime of 5 and g prime of 2 are in these positions. If they're the same thing, if we subtract two things that are equivalent, we get an answer of 0. The slope of our secant line is 0. So by the mean value theorem applied to the function g prime, there must be a value, and they call it k, there must be a value k in between 2 and 5, where the slope of the tangent line to g prime, or the second derivative, equals 0.